Hello and welcome to the first lecture in AP Chemistry. This lecture is going to deal with the review, and we're going to begin with the review of significant figures. If you remember, significant figures are used to accurately convey the accuracy regarding a certain measurement. Now I'm going to put three numbers up on this board, and we're going to discuss how to find the significant figures of all three of them, and that should do the job of reviewing for this. 30.93, and lastly, 0.030. Now, the trick that should be used rather for significant figures is to simply put the number in scientific form. So I'm going to go ahead and do all of that. That's going to be 10 to the first, because that's just going to be the same. And the trick about scientific form is it can only have one digit in the numerator. So this is going to be moving it over 1 decimal point times 10 to the first, multiplied by 10, so all it needs to be done. And now 3.0 times, because remember, we have to use the numbers at the end, times 10 to the negative 2, I believe, because if it's 10 to the negative 2, moves it over 1 spot, 2 spot. Yep, that's correct. So now, let's take a look at the numbers that are resultant. Here we have three numbers. Therefore, we have three significant figures. I'm going to write sig figs there in abbreviation. Here we have 1, 2, 3, 4 numbers. So we have 4 sig figs. And here, because we only wrote down 2 numbers, despite having 1, 2, 3, 4 numbers, we only wrote down 2, ergo we only have 2 sig figs. And you can simply define sig figs. All you do is convert the number to scientific notation. Now we must do something with dimensional analysis. And dimensional analysis is the process of using conversions to convert units. So let's say I wanted to go from grams over centimeters cubed to kilograms of meter cubed. Well, we'd have to use dimensional analysis to do this. So the first step is to create conversion factors. And I'm going to begin with dealing with the grams, the numerator. So grams on the bottom, kilograms on the top. Why kilograms? That's the unit we're going to go to. Why grams? Because if you remember from algebra class, to simplify a certain equation before we solved out for it, if a number was on the top and the bottom, then we can simplify or take something out. So if it was 4 over 2 times 2 over 2, we could take out the 2's. We could take out the 2's and become 1 over 1. Similarly, we take out the grams because we can treat these units similarly. So now, in 1 kilogram, how many grams are there? In 1 kilogram, there are 10 to how many power grams? Well, to do that, we're going to actually need to use something called kids have dogs, but dogs cost money. That's our cool acronym to remember the units. So we're starting with grams, our base unit, and we have to get the kilograms. So we're going to go 1, 2, 3. So 10 to the third is what happens now. But is it positive or negative? Well, let me ask you a question now. Are there a lot of grams in 1 kilogram? Yes, there are. Therefore, it is positive, because if it was negative, it'd be a smaller number. And I'm going to solve this out. I like to solve mine out one step after another. I'm actually going to go back to using blue. I'm going to keep it in blue. I'm not going to try to get too fancy here. So what happens is you take your calculator and you type in. You make sure you're completely on the home screen. And if you're using a scientific calculator, I'm going to tell you the keystrokes right now. 4.93 divided 1, 0, caret 3, and then hit enter. And then we should get that it is 0.00493, and our units become kilograms over centimeters cubed. Our grams have disappeared, kilograms remains, and then centimeters is also there. So now let's do one more unit and we should be good. Because we've already converted the kilograms, now we just got to find meters. So here we're going to put our centimeter on top again to cancel these out, and then meter on the bottom. And what we want to do is create a proper conversion factor. So in order to do this, we're going to put 1 meter And how many centimeters are in a meter? We're going to go back to here. Be careful. We're at centimeters, and don't go right. That's millimeters. We have to go to meters. So 1, 2. There's 2. So it's got to be 10 squared. But is it positive or negative? I'm going to leave it over here. Is it positive or negative? Well, I'm going to ask you a question. In 1 meter, are there a lot of centimeters? Yes, there are. If there were not as many centimeters in 1 meter, then we do negative. But there are. And if you're asking why I didn't put it on the number on the bottom, you technically don't have to. You can do it on the top or the bottom, whatever you see fit. You can, number. You have to leave the units on the top and bottom, but you have to use the number. So before we begin this, though, just think about it. Are we going to really accomplish our goal of going into kilograms over meter cubed by doing this? No, we're going to go into kilograms over centimeter. I don't even know what we're going to go into. We're going to go into like kilograms over centimeters squared meter or something like that. It's a crazy unit. Why? Because these centimeters are cubed, but are centimeters in cube. Now we're going to have to cube it. So by cubing it, we're going to put 3 here. And this is going to become 6, actually. Because 2 times 3 is 6, properties of exponents. And these are also cubed. But we're going to forget about the 1 being cubed, because that's still the same. Now the centimeters cancel. And then we're left with, we're going to ignore this 1 again. We're going to have to multiply this number. So I'm going to take the answer already on my calculator. I'm just going to hit the multiplication sign, 1 0 caret 6, enter, and then we get our answer to be 4,930 kilograms per meter cubed. Next up, we're going to talk, the next part of the review is to discuss naming compounds, and in order to do that, we're going to have to deal with the periodic table, which is why I have it up. First, we're going to begin with naming ionic compounds, because they're always the easier ones. And let's say that I had NaCl. First, we had to figure out which one's the positive. What are the charges of each? Well, this is positive 1, this is negative 1, so we write it like that. And the negative one always gets the ides, so it becomes sodium chloride, therefore. Sodium chloride. And let's do a different one. Let's not make it so easy. That was a little easier. Let's do AgNO3. Well, we can recognize that this is a polyatomic, and you should recognize this is a polyatomic. You're going to need to restudy your polyatomics otherwise. And this is going to be minus. This is going to be plus. How do we know it's minus? Again, it comes with the polyatomic. So this is called nitrate. What is Ag? Ag is actually silver. Ag is silver. So then we get silver, but we know that this is a transition metal, so we got to have some charge for silver. Well, the charge goes right here, and that's just 1. Silver, 1, nitrate. Next, we're going to want to deal with CuCl2. Let's say we had CuCl2, and we have to try to write a name for it. Well, the first step is to figure out the charges of each. Cu could be anything, but Cu could be not anything. There's more than one option for Cu, but Cl2 is only going to be minus. It only has 1 charge. So if Cl2 is only 1 and it has 2, that means the total charge of the Cl's in this compound is 2 minus. So to make this a neutral compound, then copper has to have a charge of 2 plus as well. And then therefore it becomes copper. But as we know, copper is right here, and it is a transition metal, so we have to put the charge. Copper 2, and then is it chlorine? No, it's chloride, because this is the negative ion. And that's ionic. Very simple. And this goes opposite as well. Let's say I have, let me make one, iron 3 oxide. Well, we know that iron is Fe, and if it's 3 over here, that means the charge of this is 3 plus, and then the oxides, oxygen is always 2 minus. We know that because of the trend. This goes 1, 2 plus, 3 plus, 4 plus, 4 minus, 3 minus, 2 minus, 1 minus, and then 0 minus. So then what we got to do now is we have to swap the charges. Simply matter of swapping these over, and then we'll be good. So then we get Fe2O3, iron 2 oxide. Now let's do some covalents. And covalent compounds don't even deal with charges. They simply are, let's do sulfur hexafluoride. That's the first compound that we're given. We have to try to name it. Well, let's use this little conversion thing that we're going to try to think of right now. Let's see if you can sit there with me and we can figure out these prefixes and the number that they associate with. So I'm going to type prefix, and then number. And I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, and then 9. Now, let's see if you can name these with me. Mono, di, tri, tetra, penta, hexa, septa or hepta, octa, nona, and then 10, listen down here, is also deca. If you don't know these, you might want to study them because they are very important. So now we get sulfur is, the unit of sulfur is S. Hexafluoride. Fluoride, F, is over here. Fluoride, F, fluorine. And the hexa is 6. So it's SF6. So let me do one now. Let me give you one. What is this compound? Well, dinitrogen means 2, so N2. Difluoride means F as well, 2. So that's our unit. That's F2, N2, F2. Let's do one more. This is technically it's called carbon tetrahydride. Well, it has another name for it, but that's the technical name as far as naming these compounds are concerned. Let's go for another one. Let's do dinitrogen oxide, and this should be ringing a bell. Okay, we have 12 minutes. We've killed 12 minutes. This should be ringing a bell. You should feel very confident with your ability to do this. Now, I'm actually going to copy this periodic table, and we're gonna copy that, and we're going to bring it down over here. And the reason being for that is because we're going to be using it right now. We're going to be using it right now when we're dealing with stoichiometry. Now, let's say we have water and oxygen mixed together to form water. We have to first write an equation for this. So water, and we know that there are diatomic atoms that exist. A popular acronym is Hankel brief, and these stand for all the diatomic molecules. Molecules only exist with 2 compounds, and you learned that back in a chemistry 1. So the Hankel briefs, which means HONCl, Br, I, and F. Hankel briefs. All these exist only in pairs. So hydrogen exists as a pair. Does oxygen exist as a pair? Yes, it does. Yields water, or dihydrogen monoxide. Which means up here I made a mistake. This should be monoxide. Dinitrogen monoxide. That's embarrassing. So this means that this is H2O. But is this chemical equation balanced? The answer to that is no, because we see we have 2 hydrogens over here, but only have 1 oxygen. So to cancel that out, we're going to do 2 over here, which settles that, but we have 4 hydrogens, so we're just going to put a 2 over here. And how is it balanced? Well, 2 is 4, 2, 2. Yes, everything's good. Everything's nice and balanced. So we've balanced our chemical equation. Now let's do some stoichiometry. Stoichiometry, which is basically just calculations in netting for net theoretical yield. Let's say let's say we were at STP. and I had 5 liters of oxygen, and I had 2 liters of hydrogen, how many grams of water would form? Well, the first step in stoichiometry in these kind of problems is to figure out a limiting reagent. So first step, find a limiting reagent. So we can just do that with anything. Well, we know we have 5 liters of oxygen, and we know we're at STP. What does STP mean? STP means an STP, 1 mole equals 22.4 liters, and mole is mass, liters is volume. So that's a thing relating volume and mass. And we can use that because we know we're at STP, which means we're at 1 atmosphere and we're at like freezing point. So 22.4 liters goes on the bottom, remember, because we're going to delete rid of this, and we have 1 mole of O2 at the top. Well, we're not going to worry about O2. That's going to be regardless. So 5 divided by 22.4, that equals 0.223 moles of O2. So let's just draw a line right here. Let's just go down here. Now that we're in moles, as opposed to previously when we were in liters and we couldn't use something to relate this, now that we're in moles, we can relate the number of oxygen molecules to the number of hydrogen molecules by the ratio that for every 1 O2, there's going to be 2 H2, given by our equation. We've balanced it, so we know that that's how it works. You might remember that from chemistry as well. And now we multiply this by 2, and we get that we should have 0.446 liters of hydrogen. I'm bringing it down over here, of hydrogen, in order to make this reaction work. Well, do we have 0.446 liters of hydrogen? Oh, wait, moles of hydrogen. Sorry, this should be in moles of hydrogen. We know that we need to have 0.446 moles of hydrogen if we want to react 5 liters of oxygen. So do we have that? Well, we can figure that out by doing our conversion. 1 mole equals 22.4 liters. Moles cancel. Multiply that by 22.4, and we get that we have 10 liters of hydrogen necessary. So that's definitely not how it works. 10 liters of hydrogen, where we only have 2 liters. So this number means absolutely nothing to us, and we found our LR, which is hydrogen. The next step after we find the LR is to use LR to convert. So in other words, we got to use our LR, which we found to be the hydrogen, so the 2 liters of H2, which we're going to convert into moles right now, is by saying that 22.4 liters and 1 mole, liters cancel, 2 divided by 22.4, 2 divided by 22.4 is 0.089 moles of H2. Now we go from moles of H2, which is something else that we know, into something else we don't know. So 2 H2 for every 2 H2O. How did I get this? Recall that it's from the balanced chemical equation. So H2 cancels, and now we're going to be left with moles of H2O. Now, if you notice, we're going to multiply by 2 and divide by 2, which is exactly the same thing. So we're going to get the same answer. So let's just rewrite that. 0.089 moles of H2O. Now, that's how many moles of H2O we're going to need, but they're asking us about grams. So this is why I just chose this problem, because now we have to consider molar mass. And molar mass is basically the molar mass of H2O, the mu of H2O, big mu of H2O. Nu is basically the letter for molar mass. It's like a variable. It's like a set-aside variable, like pi. Nu is the letter for molar mass. So now we have to find that by multiplying all these other molar masses. So 2 times 1, you might also remember this from chemistry 1, O, 16. You might not be able to see that, but rest assured this O over here is 16. So 2 plus 16, that's 18 grams. So in 1 mole, there's 18 grams of H2O in 1 mole of H2O. So then we can use that conversion factor, 18 grams in 1 mole. Mole goes on the bottom, so it can cancel, and then we multiply that by 18, and we get that after all our hard work, we're going to get 1.607 grams of H2O final. Now let's do something else. We got 1.607 grams of H2O, that's good. But let's say we wanted to find out how many molecules of H2O we're going to get. Well, to do that, we're going to use the same number, 0.089 mole H2O. But instead of going from moles into grams, we're going to go moles into RP, representative particles. Well, what 1 mole is defined as? 1 mole is defined as 6.02 times 10 to the 23rd representative particles of anything. So we're going to multiply this 0.089 times that number. I'm just going to draw a line right there because I don't feel like rewriting that. And then it's going to be 6.02 E23. I'm typing what I'm typing on my calculator. E is second. The letter right above the button right above the 7 in your calculator. There should be a comma, and that should be E. And then we get that we're gonna have made 5.3578 times 10 to the 22nd H2O molecules, which, if you don't know, an H2O molecule looks kind of like this. You probably no, doesn't look like that. I meant to draw that. Looks kind of like that. We're gonna have a lot of those floating around, and basically that constitutes everything that you should have in the back of your brain and be able to do really quickly in AP Chemistry. So I'll see you guys in the next tutorial, in last lecture rather.